So yesterday we discussed about the PMMC, permanent magnetic moving coil. About this here, how we are going to be converting a micrometer to a few range ammeter, as well as the micrometer to a voltmeter, as well as the ohm meter also, that we have been discussed yesterday's class. Today we can go for the digital measuring instruments. Okay. So DVMs, that is digital voltmeters are there. So how we can measure the and how fast it can gives you the whenever such a input which is going to be giving to you, how fast it which can gives you in such a manner, how it is which a accurate values which are going to be giving out to you. That we will discuss about the based on the here digital voltmeters. Okay. So the thing is that here previously the analog meters which can be replaced by the digital voltmeters here. So those are very cost is very high and which may not give you an accurate values, but we are going to be measuring those values. Uh, and the thing is that here the time taking is also very high to give the output values. So in such a way that by using such a technology and replacing the analog into a digital, within a fraction of time it can gives you the output value, whatever the desired value you are going to be giving required, that values are easily you are getting within a fraction of time. Okay. And also these are also nowadays, these are also very cheaper than that of the analog measuring instruments. Okay. So let you go for this here. What are the principles which are going to be involving in this? So these DVMs which are classified into ramp type, integrating continuous, balance, successive approximations. So there itself it has the oscillator generates the clock pulses and which are going to be allowed to pass through the gate a number of decade counting units, and also a sample rate multivibrator which is determines the rate at which the measurement cycles are initiated. And one of the method to reducing the dependence of the accuracy of the conversion of the resistor capacitors. So resistor capacitor means here the whenever you are using an operational amplifier, resistor capacitor which is a integrator. Okay. Which is used as a technique called a dual slope converter. Let us discuss about the digital voltmeter and how the DVMs are classified here. The DVM displays with measurements of either DC or AC voltage, and instead of the pointer deflection of the continuous scale in an analog devices. So they reduce the human reading errors. Okay. And interpolation errors, eliminate the parallax error, increase reading speed, and often provides outputs for further processing or recording. The DVM, which is a versatile and accurate instrument which develops the integrated circuit models, the size, power requirements, cost of the DVMs drastically reduced here, and the outstanding quality can be illustrated some of the operating performances. Input range is from plus or minus 1 volts to plus or minus uh, 1 crore. That is with automatic range selection and polarity And what is the accuracy? Plus or minus 0.005% of the reading. And stability, which is very high in short term, that is 0.002% of reading for 24-hour period. Resolution, which is also very high, 1 part of 10 power 6. 1 microvolts can be read on the 1 volt input range. Input characteristics. Input resistance approximately 10 mega ohms. Input capacitance is 40 picofarad. Calibration, internal calibration stabilized reference source allows. This depends on the measuring circuit. Output signals. Print command allows output to printer. That is a BCD, binary coded decimal output. Also available for digital processing or recording. Next is the optional features included additional circuitry to measure the current and resistance. So the DVMs which are classified in 4 types. One is the RAM type DVM. That is a linear ramp, staircase ramp. Another one is the integrating DVM. Single slope and dual slope. Next is the continuous balance DVM, successive approximation DVM, digital. So now we can go for the linear ramp type DVM. So what is the principle of the operation which can be involved in this? That is the here DVM, which is based on the measuring of the time it takes for linear ramp voltages to rise from 0 to the level of the input voltage, or to decrease the level of the input voltage up to 0 volts, increase or decrease. So the time interval which is measured with an electronic time interval counter, and the count displayed as a number on the digital display which is going to be using in the DVS, and the conversion voltage to a time interval at the start of the measuring measurement cycle. The ramp voltage is initiated and the voltage can be positive or negative continuously compared with the known input voltage. So at the instant the ramp voltage equals to unknown voltage and it is coinciding the circuit or comparator, and it can generate a pulse and which opens the gate. This is the case. So call clock pulses to counter here. Voltage time conversion using a gated clock pulse. So the gating time interval is given out here. This is the starting measurement, and here it is coinciding here and here. This is the ramp like that. So here the ramp wall is continuously decreasing the time and it finally reaches the 0 volts. And second comparator here. This is the input comparator, ground comparator. Generates output pulse here. Okay. Which is closer to the gate here. This is the gate. The oscillator gate which is connected to the counter, and here it is recording. This is the sample rate, and here ranging and alternating attenuators. These are the comparators here, op amps. So whenever an oscillator is generating a clock pulse here, this one, and which are allowed to pass through the gate to a number of decade counting units. So the number of pulses passed through the gate are displayed by the display. So a sample rate multivibrator determining the rate at which the measurement cycles which are to be initiated, and circuit which is providing an initiating pulse for the ramp generator to start its next ramp voltage. At the same time, that reset pulse generated which turns into the DCs to the zero states. Next is the staircase range type DVM. So it is modified from the ramp type DVM, but in somewhat simpler in over all designs. So this is a moderately priced here. And the DVM makes voltage measuring input voltage, comparing the input voltage in internal generated state is that. So which contains a 10 mega ohms input attenuator, and it may provide the range from 100 millivolts to 100 kilovolts full scale. The DC amplifier attenuator, which are providing the 5 input ranges. And the DC amplifier, which is fixing the gain of 100, delivers the 10 volts to the comparator at any of the full scale voltage setting the input potential divider. And the comparator senses coinciding between the amplified input voltage and the staircase ramp voltage, and which is generated as the measurement proceeds through the cycle here. So the cycle first initiated the clock at 4.5 kilohertz relaxation oscillator, which are providing the pulses to the 3 DCs cascade. The range causes a front panel indicator light up the input capacity, and the instrument has been exceeded here. The output of the D2A converter, digital to analog converter, are connected in parallel and provide the output current proportional to the present outs of the DCs. So the staircase amplifier, which may convert the D2A converter into a staircase voltage, and which are applied to the comparator. And the comparator senses and coinciding input voltage. Staircase, it provides the trigger pulses to the stop the oscillator. The present content of the counter is proportional to the magnitude of the input. Sample rate. Here the disadvantage of this type analog to digital converter requires precision ramp to achieve accuracy. It requires the precision, stable capacitor, resistor, and the integrator. Circuit is reversed. Print mistake. See here. Input signal, input attenuator, DC ampere amplifier. There is a comparator here. Here comparator flip-flop 4.5 megahertz kilohertz oscillator. 2 kilohertz is simple as sample oscillator, transfer amplifier, reset amplifier. So here unit decades of counters are there up to the crores over the range of flip-flop. Tens decade, 100 decade. Here also DTA converter for units, tens, hundreds of the range. So there is a reset line, and this is the reset amplifier, which is connected to the comparator here, flip-flop. And which is transferring the amplifier here, which is connected to the transfer of line. and to the digital display. It may gives you the output here. Next is the dual slope uh, type DVM. So this is the one of the method for reducing depends of the accuracy of the conversion to the resistor capacitor and op amp, which is used to technique which is called the dual slope converter. This is integrator actually, capacitor and resistor. Yeah. So yesterday we already talking about this. So this is an integrator which is used to integrate an accurate reference voltage. This is the reference voltage. So inverting terminal, in series there is a resistance input voltage. Non-inverting is grounded. So the same integrator which is used to integrate with the reverse slopes, the input voltage and the time required to return to the starting voltage which is measured. So it does not matter which of the two integrators occurs the first for the understanding unknown voltage. Integrated first and the reference will be considerable as. So this is the slope V minus Vi by Rc. This is the plus Vi by Rc. Rc is the time constant, 0 to T. So in this Vx is the steady input voltage related to the ground, and V out which is the output voltage from the integrator. R and C is the time constant. Why? Because the tau equals to RC, time constant. At T the elapsed time which the integrator begins. So from the above equations, if you are going to be doing some calculation part, you may get it like this. So complete dual slope A to D converter. So there is a switch is there, uh, zero correction, which is a automatic zero correction. This is with any analog system, amplifier offset voltage, offset currents and bias currents, the leakage current of the capacitor, which can cause in the dual slope A to D converter. Capacitor, resistor, non-inverting is grounded, inverting is connected to the switch here. So this is an integrator, the output of the op amp which is connected to the indicate, and there is a clock generator, and this is the count connected to the current counter, and there is a display. The thing is that here again which is fed back through the switch here, reference voltage. The reference that is equals to this. Okay. Next is the success approximation time, which is I just want to show you dual slope type SVM. You can go through the single slope and dual slope DVM. Dual slope ADC. Yeah, this is the V reference voltage. Yeah, this is integrator, capacitance and resistance. So this is the inverting terminal and this is a non-inverting which is grounded here. It is again connected to the comparator here. Yeah, output of the comparator which is given to the AND gate here. There is a clock here. Yeah, if it is high, 1 means high, 0 means low. Counter is reset to 0. Yeah, the output of the integrator which is less than the input voltage. Okay. So in this particular case only you are going to be changing all these. Yeah, 1.0 is 0 and gate. Single slope A to D convert. Temperatures. So due to the accuracy of the single slope, A to D ADC is very poor. So ADC is not used for the measurement purpose. Using the dual slope ADC. Okay. To understand this working here, we input a reference here. So the thing is that uh, how it is going to be working for the dual slope ADC. Now this is the integrator here. Input voltage, V reference voltage is there. V input into DT. Integral dt is t by substituting t1 by RC into dt. Negative reference voltage is there. So here the magnitude of reference voltage which is larger than this. So this is the V minus input by RC and this is the V reference by RC. This is T2. into minus V reference voltage. Like that, you can easily calculate the how to calculate the output voltage of this. So this is the case. What I mean is how I shared this video is because of how to calculate the reference voltage, output voltage. Why it is getting minus V I by reference uh, RC, and here V reference voltage by RC positive. This is for T1 and this is for T2 time T. Okay, I think so you got it. Like that, by substituting you may get this one, this equation, output voltage. This is the equation. This is a complete dual slope A to D converter. Here also there is an electronic switch is there, a reference voltage, and which is again connected to the ground, and there is an integrator is there, that is operational amplifier, resistor, capacitor, again which is connected to the AND gate. The same thing previously what we discussed. Count is there, there is a counter, and there is a reset pin which is connected to the control logic, and there is a clock generator which is connected to the AND gate, and based on the reference and input voltages, how the integrator which may gives the output values, and which may be connected to the counter here, and which is going to be displaying. Next is a successive approximation type DVM. This is a very effective and relatively cheaper method of analog to digital conversion. So that is the method of successive approximation. This is an electronic implementation technique which is called binary regression. So to determine the value of number, and it is allowed to make the estimate. The estimate would be evaluated and it would be known if the estimate is equals to or less than that of or greater than the number which is determined, and the maximum and the minimum values are possible which are also known here. So there is an example which is going to be given out between the 0 and 5 level. So input operational amplifier which is connected to the DTA converter, and SAR is their successive approximation register. If it is greater than or less than the top, again connected to the decision logic. There is a clock and clear. So next is the simple frequency counter. So which may stands of time and frequency, which is essential. Uh, they may be transmitted by the radio from one location to the another location without the actual movement of the standard. So it is possible to have a traceability to the primary standard without difficulty. And the primary standard which is related to the structure of the matter, and primarily standard can be easily duplicated throughout the world to allow high accuracy measurements anywhere, because the relative case with which frequency and time can be measured to great accuracies. Electronic system which are developed around the capabilities. The tolerance expected of radio transmission equipment and the spectrum which is required by the voice modulated to our radio transmitter using the modulation. What is the order is there? That is 15 kilohertz. And this is going to be here the frequency of the transmitter which can be carried out. Carrier would be held to absolute precision to a communication channel, and which could be signed every 15 kilohertz, and make the most efficient use of the radio spectrum. Because of the accurate measurement techniques which are available and standard can be made available. So the communications channels which are assigned for every 20 kilohertz in the UHF. So here this is going to be requires a carrier frequency accuracy and stability only 5 kilohertz, which is approximately 0.001%. And it is easily achieved with modern frequency control and measurement techniques. Although relatively stable frequency, which is standard, have been many years. And the frequency measurement required precision standard frequency comparator and interpolation oscillations. So here the input signal uh, coordinating here. This is an AND gate here. Counter is the display memory. JK flip flop. The Q bar which is pin connected to the reset, connected to the counter, and the latch which is connected to the display memory. Again, so this is a crystal oscillator for up to 1 megahertz signal conditioning circuitry. Can we go for the simple frequency counter? Wait a minute. I just want to show you the. Let you go for the first is what is a counter. The counter counts the number of times of specific event has been occurred. So yeah, digital input. If the event is not in digital form, then the first it is needed to be converted into a digital form. The counter, yes, digital input pulses. So the counter detect the high to low or the low to high transition. This is 0, 1, 0, 1 like that. This is the clock pulse. It can be originated from the some external source. And these pulses are arriving periodically. It may arrive in this. So and the counter is going to be registering them even and the increment its current count. So it is counter or interconnection of the flip flops. These are the flip flops. Yeah, for 4-bit binary counter, 4 flip flops are there. This is the downward counter. 11112 000 is the binary down count. The modulus of the counter, which is the number of different output states through which the counter goes through before returning to its first state, known as the modulus of the counter. So I am giving the only idea about the here. What do you mean by a counter here? Yeah, 2 power 4. 2 power 4 means 16. Here you may get the 16 combinations here. The year counting, counter applications, time measurements, analog to digital converter, frequency division. The decoding logic is also going to be connected here. So the decoding logic, which is designed in such a way that it generate the logic high when the output of the counter goes to the 100 count, and at the same time it is also reset the counter to the 0. This means that the counter we can generate the periodic pulses at every 100 microseconds. So the counter we can take the specific action in the predefined time. Yeah, what is the time duration between these two pulses? Yeah, with the help of the flip flop or other, we can generate the time pulses. The time difference, the duration of the difference between two pulse sizing edges. Frequency is 1 megahertz between the two time pulses. Yes, A to D converters. Yeah, just now we discussed about the dual slope, ADC. Synchronous, asynchronous ripple counters. Yeah, the output which is connected to the input clock. This is synchronous count. All the clocks are which are connected at the same time. That is synchronous. Asynchronous is output which is connected to the input of the clock. So like that you need to understand the simple frequency counter here. This is a counter. How the flip-flops, whether it is a synchronous or asynchronous. Synchronous, this is asynchronous clock which is connected. So what is the final summary of this one is that uh, here the design consideration of all the DVMs, the digital frequency meter, which are thoroughly uh, discussed in the complete mathematical background is needed. So at the instant that the ramp voltage which are equals the unknown voltage and a coincidence circuit or the comparator generates the pulses and which opens a gate. The number of pulses passes through the gate are displayed by the digital display and the sample rate is controlled by sample relaxation oscillator. The display circuit store each reading unit until a new reading is completed. It is going to be eliminating any blinking during the completion. The dual slope method is slow, but it is quite adequate for the digital voltmeter used for the laboratory instruments. Here, give the circuit diagram and design for lamp linear. What are the advantages of staircase? Give the principle and working of a dual slope DVM. Expected question. What is the disadvantages associated with the single slope? Okay. So this ends out this. And by coming classes, we will go for the digital electronics. Every class which is discussed with the help of the PowerPoint presentation only. From the PPT itself, I am going to be explaining this. Number system and digital logic gates. That we will discuss in the coming classes. That is the digital electronics. Block 3 and block. We can conclude it. How to read out and how to go for. Okay. Right. Thank you.